Good morning, everyone.
Good morning, sir.
Okay,
Good morning, sir.
so today is our last day for summer school, and in this morning session is going to be a bit light session. So, what mainly we are going to do in this session is Jigar and Pratik will plot some interesting fractal plots, okay, and they will show you things. But before that, I will give very small part of nonlinear dynamics, how computational physics can be used for that. In fact, nonlinear dynamics can be done only using computational physics because analytical methods have their limitations. So what we shall do is we shall look at a few problems, and then we'll go to those fractal patterns and we'll see the relation and other things. So let me share this Excel. Okay, let me first share the PowerPoint window to explain few things. I hope this is now coming.
Yes, sir.
Yes, sir.
So when we talk about first we're going to talk about, this is not nonlinear dynamics directly. We're going to talk about damped and force oscillator. We had earlier last week talked about damped oscillator. Now there is an additional term over here, which is a driving force, and this driving force may have a frequency different than the natural frequency of this oscillator. We had also seen with one of the example that as the damping term changes, okay, the time period may change. And we had also considered one example where the actually oscillator was non-linear oscillator, though we didn't specifically mention that. He said that if you have oscillator with like in simple pendulum, you have oscillator with force proportional to sine theta rather than theta, or in that case torque is proportional to sine theta in place of theta. And if angle becomes large, then in that case what happens to the amplitude? And we saw that even the frequency gets affected when you do that. Okay, so now we will be talking about damped and force oscillator. So in damped force oscillator, we just have to add one term. Rest of the things remain the same. We are still going to use the Euler's method to solve this differential equation. So let us go back and check in Excel what we can do. And of course, it is an exercise for all of you that you can translate it into Python. Now that you are quite confident about using at least basic Python codes to plot things. So let me share the Excel window here. So here what you observe, if this is visible, is this visible?
Yes, sir.
Yeah. So here what we have done is, it is the same code that we are talking about. That velocity is going to be addition of the earlier velocity acceleration to delta t. Similarly, the displacement is going to be the earlier displacement into velocity multiplied by delta t. The Euler method we are talking about. Only thing is acceleration is going to be based on certain additional factors, and that will be if I click on this. Okay, this was the sine term that we talked about. Now suppose I don't want to do that. I want damped force harmonic oscillator. So I said okay, let me write the force is going to be minus kx, so minus k, and k is in d2, so $d$2, that is to log the cell multiplied by x, okay, minus $e$2 multiplied by v. Okay, so minus kx minus bv, and we need to write one force term. Sorry, the acceleration term is here. Yeah, the acceleration term is here. So it is already written minus $d$2 into E phi. E phi is nothing but time. Sorry, E phi is nothing but the displacement over here. Okay, minus $e$2, which is b into d phi. D phi is nothing but velocity, and there is an additional term of b6. I'm just going to remove this. So there is a b6 term. Let me. What is this b6 term? B6 term is nothing but this driving force, and that force term you can see is sine of this omega f into t. A phi is t. Okay, so if I click here, you see which cells get selected. So it is amplitude of the force and omega f multiplied by at. Now, right now I'm keeping amplitude, the driving force amplitude 0, omega also 0, and what we shall get is the damped harmonic oscillator term. Okay, so the plot is already there. I just hidden the plot down here, but you can see the plot. This we had already seen earlier. Now what we are going to do is, so what is happening is it is starting at this particular amplitude, and then this is the phase space plot, and it spirals in. Okay, now we are going to add this term of force amplitude. Okay, so let us suppose I keep force amplitude initially say 1, and the frequency of force. Okay, I'm not going to keep exactly same as omega, but let me keep 0.5. Okay, why? Because root of k by m decides the angular frequency, and k is taken as 1, m is also assumed as 1. Okay, and therefore we know natural frequency of the oscillator was 1, but I'm keeping this damped harmonic oscillator frequency is 0.5. Okay, so when you do this, what you observe initially there is a transient motion. So you see some chaotic lines over here. Okay, but ultimately it comes back to this. You see the big pattern. Okay, so this is a phase space. This is an ellipse showing that ultimately this oscillator is going to stabilize on. It is going to stabilize on simple harmonic oscillation. Okay, so I can change the frequency, and you can look at the amplitudes. The amplitude is somewhere between after stabilization, it is somewhere between within 1.5, and here it is somewhere around 0.6, 0.7. Okay, I mean the vertical axis is of course is the velocity axis or the momentum axis, and the horizontal axis is going to give you the displacement. Now let us change the driving frequency to say 0.8. So it is now closer to the actual frequency, the natural frequency of the oscillator, and you observe that the stabilized displacement is quite about 3, which means it has really increased by large amount. Okay, and if I take it larger than damped oscillator, force oscillator natural frequency, again you see it is slightly more than 2. If I take it 2, double the frequency, you see there are going to be initial transients, but ultimately, and there is also damping. Okay, so ultimately what happens is it settles down on this particular ellipse. Okay, and you get because you are continuously providing energy, so ultimately it has to come down to some particular amount of energy. Remember last time we said that this area under the this entire area within this particular loop, or we say the volume in the phase space, okay, is proportional to energy of the oscillator. So ultimately it is coming to one particular fixed amount of energy because you are driving it with certain force. Okay, so but whatever you observe, whatever may be the frequency, even if I take frequency 5 times, okay, ultimately well, now it has become very small. So let me increase the amplitude of driving force. Let me make it large. Ultimately, you will see that the final pattern is still an ellipse. Okay, and what I have done is out of the 10,000 oscillations, the last around 1,000 points I have plotted down as displacement versus time graph. So let me just bring that up. So what is happening here is this. Just a minute. So what is happening here is this is the phase space on the right hand side, and this is the time domain graph. Okay, x versus t graph, and you see that it is nice sinusoidal graph. What has happened is it has ultimately accepted this particular frequency. Okay, omega f equal to 5. Suppose I make omega f equal to 3. Okay, you will see that this frequency is reduced because ultimately what happens is the natural frequency dies out because of this damping, and the oscillator oscillates with this force frequency, and the energy and the amplitude is all sinusoidal. Okay, so this is forced oscillator. Now we come to the next concept, which is non-linear oscillator. So let us look at the slide, and if you have any difficulties at this point, you can ask. So this was a slide for the driving force and force dam oscillator. Now we go to non-linear oscillator. So there is an additional term here. Okay, so what you have is minus kx restoring force, minus Vb is a damping term. The driving force term is also there. Plus there is a non-linear term over here. Now this non-linear term you see is proportional to x cube here, and the alpha will have some amount of alpha is going to be a coefficient. Okay, so basically this alpha actually indicates in the standard textbook this alpha is included within k plus some additional coefficient, but I'm writing separate term over here. Okay, so what does this do? This term basically gives additional frequency component that we'll see. Okay, and that makes the entire system non-linear, because you see this is non-linear equation. There is a different power of x involved here in this particular differential equation, and analytical solutions really become difficult, and therefore people go for computational techniques or numerical methods. So let's simulate this. So we only have to add now this extra term. Okay, so let us do that and see what are the implications. Let me share the Excel sheet. And now I'm going to add this alpha term. I'm going to make this alpha term non-linear. Okay, and instead of, and of course I have to add that term in A also. So let me just add that term. So minus alpha is F2. So $F $2 multiplied by x cube. So this is the earlier step x cube I have to take, and then I iterate this till the last point, face this equation. Okay, right now alpha is 0, and therefore you see there is no change here. I hope this is still visible. So now let me increase the value of alpha. Let me make it 1. Okay, and what you observe is there is small change. The shape of this ellipse you see changed. Okay, when it was 0, the shape was different. Okay, so you see the velocity remains the same, but displacement has changed here. Okay, so velocity was between plus minus 2, that has effectively remained the same, but the displacement value has changed. Now I increase this, so make it 2, and you will start observing that now this is not nice ellipse. Okay, let me just keep this aside down. Now this is not nice ellipse. Okay, it is more like, there is a kink is effectively getting generated somewhere over here. You see that it is not curved out, it is slightly curving in. Okay, let me just add people. Then if I increase this alpha further, this is non-linear coefficient I'm increasing, and you observe similar kind of thing. See, ultimately, wherever there is a dense thing, the oscillator has settled at that point. So you can see the last few oscillations, okay, they are like this. Okay, I make it larger, say 3.5. Okay, I make it further large, say 5. And you see that this nature has not changed much. Okay, now what we shall do is we shall increase the amplitude. Okay, you see the amplitude is still remaining within, say, about plus minus 2. Okay, the horizontal this thing. So now let me increase this external frequency, driving frequency. Okay, say I make it 5, and you start seeing something. Okay, let me reduce this. You start seeing something. What do you observe? There are two things you observe. In the phase-space curve, you observe the kinks. Okay, so what has happened? The nonlinear term I have increased, but not, when the external driving frequency was less, okay, even when I made this phi, it didn't have much big effect. Okay, when, say, for example, okay, let me make this small, the external driving frequency, and make alpha phi. Okay, it had some effect. If external driving frequency was say a different value, okay, then it was not having effect. So for certain frequency, you see that you start getting an effect. So here you see, for example, there are certain kinks coming into picture. Okay, I go to omega f equal to, say, 3.5, and I don't get that much. But if I increase frequency even larger, something like 5, and if I make even alpha 2, small, still you see that there is a kink observed. What does that kink mean? When it comes to displacement versus time graph, you see that this is not a nice sinusoidal wave, okay, as if there is additional frequencies appear. Now this additional frequency, so here itself on the phase space curve, you can observe that it is basically an ellipse which is superimposed on something like figure of 8. Okay, I mean one twist on top of ellipse will give you something like this. So there is additional frequency component coming over here, and this additional frequency component that you observe, you can also check in the Fourier analysis. Okay, so what you can do is, I mean, just by making observing this, you can find out, but you can also check that when you do the Fourier analysis of this last part, when the oscillations are effectively settled, okay, you get those extra frequency component. But right now what we'll do is we'll see by changing alpha value what all things can happen. So suppose I make alpha, that is coefficient for nonlinear term, as, say, 2.5. okay, you see that this becomes more prominent, and the kinks here become more prominent. I make it 3. Okay, again you see the kink has become even more prominent. Okay, but this is not going to be true for all frequencies, all driving frequencies. So certain driving frequencies, it starts getting excited. That is what an interesting part is. See, for 2, it is, for driving frequency twice the natural frequency, it is not excited. Okay, I make it 2.5. Well, it is not excited. I make it 3, still not excited. 3.5, okay, not excited. I'm keeping alpha, okay. So moment I make it 4, you see that it is highly excited. So there are certain frequencies one can now in Python kind of coding, one can slowly swipe, go on increasing the frequency, and see where the higher frequency oscillations start getting excited. Okay, so I'm going back to the first example that we looked at, and now what we shall do is that this part, we'll take the data, do the Fourier analysis, and see that there are multiple frequency components coming. Okay, so this I had taken last 10,000 data points. Now let me just go to that. or I had actually taken from 8,000 to something like 9,024. Okay, so let me take the E8000 to E 9,023, total 1,024 points. So I selected that. I insert a new sheet. Okay, let me just paste only values. So I right click, go to, okay, let me, I have to select that. So I select this, I go to the new sheet, right click, paste spatial, only values. So I'm only interested in these displacement values, okay, which are varying as function of time. And I will do the Fourier analysis of this. So let me go to data analysis, Fourier analysis. I need to select the input range. I select A1 to A1024. I have taken 1024 points. Okay, and let it put it in the new sheet. I'm okay with that. So it introduced a new sheet, and these are the Fourier terms. Okay, all complex terms over here. Fine. I have to find out. I can calculate what is the absolute value of these terms. So IAMABS is a function, and what I can do is I can put this in, and let me plot this. So when I plot this, you clearly observe that there are two frequency components, and one frequency component is higher than the other frequency component. That also you could have, I mean, you had observed very clearly. Okay, so I mean, this is the way one can do the analysis of things. One can play with frequency, one can sweep the frequencies very slowly and find out where the excitation of higher harmonic comes. Okay, what is happening over here is the higher harmonic is getting excited. Okay, and that happens for certain combinations of alpha values and omega values. So one can check that. Okay. So that is what as the first part I wanted to show. So now Jigar and Pratik can take over, and they can show you the different fractal patterns. What is the connection between this and that? It turns out that uh, when you have nonlinear systems, their phase spaces are fractal in nature. Now, what is fractal in nature? That there are self-repeating patterns, and then the patterns are never, the phase space curve never gets repeated. So what it does is it goes on filling up the intermediate space. So optimization of that particular space, because the amount of energy of the oscillator has not changed. It is effectively, once it gets stabilized, it remains the same. But every time it changes its motion, and in chaotic system, it tries to occupy every part in the oscillator that it tries to do. So it is observed that the phase space representation of nonlinear oscillator, when it goes into chaotic system, shows fractal nature. So what are these fractals and how we can plot them, and very nice, interesting figures you can see in Python. Okay, that Jigar and Pratik will now show you. So
Hello,
yes, yeah,
good morning.
good morning, Jigar.
So, sir, we have also done damped oscillator and coupled oscillator in Python. If that is possible, we can show that as well.
Yes, yes, you can show that also.
Okay.
So
So we'll start with that, and then we'll come to the logistics and the
so what
iterative
we were planning is
functions.
I'll first do coupled oscillators, then Jigar will show you damped oscillators, and then we'll go to logistics. Then we'll show you an on map, and then I'll show you Lorentz map, like that. Yeah. So shall I start then? Just a minute. So is my screen visible?
Yes, sir.
Okay, so we'll start with a certain example of a coupled oscillator. So how it basically is if this is a rigid support, there is one spring, then we have mass 1, there is another spring, we have mass 2, there is another spring, and there is a rigid support, like that. And what we have is this spring, the first spring will have a constant k, the second will have k dash, and then last will have k. This is the pattern that we follow. Yeah, so let's start by importing libraries. So we'll start with our mass. I'll make list of masses. We have two. Let's take same for now. Then we have k values. So we just have two k values, k and k dash. So even make a list of that. So if our k is 1 and k dash, let's say it's 0.2 for this case, then we'll take dt, say 0.01. Now we'll take our initial positions. So x initial, that is the initial position of masses. Let's say that was it at 1 and second was at 3. We'll take the initial velocities. Let's say they are 0 at the start. Now let's make empty lists to store our values. So we'll need our values. We need empty list for displacement of x1, that is for mass 1. So let's say x1 values, and our displacement for mass 2. And then let's proceed. Oh yeah, before that, we haven't made an empty list for our acceleration. We'll have two acceleration values for M1, M2. And yeah, what else will we need? That's about it, I think. Do we need anything else? X and V in A. Oh, X and V values. So we need X and V values after we calculate using A, so that we will append it in X1 values and X2 values using these. So now let's say for I in range time, okay, let's say we have time, how much should we take? 5,000. Let's say it's 5,000. Our first element that we'll have acceleration for first mass, so that will be a0. Let's write the formula for that. Now we have minus of k, the first k value, into x1, so that will be x initial first index. Then we have to subtract this. from the k dash value, because it will be influenced by others, into k1 into the distance between distance between the positions of x. So we have x in 0 minus x in 1. Let's see if the brackets are okay. 1, 2, 3. Okay. So and this whole thing will be divided by m. M of our first mass is m0. Similarly, we'll write for acceleration term for second mass. So I'll just copy this, paste here, change the index. So acceleration term for first mass will be, this will remain same. Xn will become 1. This will remain same. This is same. This is same. M0 will become 1. And this will become plus, because it will be from the opposite side. Yeah. So we got our acceleration terms now. So from these, let's take velocity. So for v0, for velocity for mass 1, it will be v initial of first plus acceleration of first mass into our dt. Let's copy that for second, change indices. You could put this in loop, but don't put acceleration in loop. It gives a lot of errors. I'm not putting anything in loop right now to keep it simple. So these indices are repeating. So 0, 0, 0 and 1, 1, 1. So you can put this in for I in range length of same masses. How many number of masses, that many number of velocities you will have. But be careful if you put everything in loop. Then you'll have to be careful about the indices for acceleration, because here they change. So be careful about this. Now for our position values, so let x0 equals to, it will be x in of first index plus velocity of first into dt, and x1 yeah. So now this is done. We need one more actually array for our time values, to store our time values as we'll go in the loop. So this is the maximum time we take that for in range. Now we will append the time values. Time values dot append I. Then we'll append our x1 values, whatever will be x0 term. And we'll append the x2 values. Yeah. So this is done. Now we are in a for loop. So we'll have to update these x0 and x1 values. So for that we'll say x in 0. Now this will become our x0, and x in 1 will become x1. Similarly, v will change. V in 0 will become v0, and v in 1 will become v1. Now if you notice that these things have the potential to be put in one single loop, because the indices follow like perfectly. So for I in range length of masses, all this can be put in one loop. So you could try that out by yourself. Now we'll see how the plot looks for this. So let's say size. And we'll plot time versus an array of time values versus our x1 values. So this is displacement of x1. So let's put a label to this is for mass 1. We'll copy this whole thing again. This is time values versus mass 2. Label for mass 2. Let's put legend. Yeah, so okay, let's increase the length. So now you can observe that the initial position
We
we have
can't
given
observe
for
the graph
mass.
properly. Yeah.
Is it not visible?
Now it is visible.
Okay.
It was only half.
Yeah. So now you
show
can see.
at least 2 beats periods, that you can see there is an exchange of energy.
Okay. So I'll increase the maximum. Let's say in 10,000. Yeah. So we could do one more thing is that we could plot subplots.
What was the initial condition? What was the initial condition?
So initial condition, the masses we kept same, and x position was 1, and the mass 1 position was 1, mass 2 was 3. So
Just
you
give,
can see.
no, start with simple case that only one mass is moved, the other is
Okay.
not moved.
Okay. So let's start with this.
Yes.
So this mass, you see, this was at 0, but when we started other mass from 1, it started transferring its energy to the second
It is
mass.
not refreshed yet for us. Now it has come.
Yeah. So see, the orange line is for mass 2. So when we displace mass 1 and leave it, the mass 2 also starts oscillating slowly. And when the mass 2 attains its highest magnitude, highest amplitude, mass 1 has its lowest displacement from its mean position. So they just keep exchanging energy between themselves, and you can observe the same pattern throughout. Now you can change the values for K between the springs and masses.
You can try one thing.
Yeah.
What if mass 2 had initial displacement of -1?
Okay. -1. So basically they're compressed then.
Yes.
Okay, interesting. I hadn't
Okay,
tried
so
this.
you don't get any kind of beat because this is called normal mode of vibration. So
Okay.
when it is moving with constant amplitude, constant frequency. Now you can imagine how you can actually count how many oscillations are there approximately. So start counting blue ones. So 1, 2, 3. I mean, you start from there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18,
18.
and 19 is almost getting completed. Okay,
Yeah.
because that blue line has almost come up.
Yeah.
Now go back and give the symmetric conditions. X1, M1, X1 is also 1 and X2 is also 1. And run this. Now the both have overlapped and you can count how many oscillations are there. 1, 2, 3,
3, 4,
no,
5.
this 3, 4, okay, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So this is completing less number of oscillations. That was 17. This is completing 16. So this is called when the system is oscillating symmetrically, it is lower normal mode of vibration, lower frequency normal mode of vibration. And when it is oscillating exactly in opposite phase, that was high frequency normal mode of vibration. And when you give only asymmetric conditions, like one is oscillating with some higher energy, other is not oscillating initially, then you get both the frequencies mixed together. That gives you the beat kind of phenomena. Okay, so you can now play with all those numbers. You can change k prime and see what happens. Give asymmetric conditions like 1, 0.
Okay. Yeah, so mass one was at rest initially. We displaced mass 2, and yeah, you can see.
Now you can change k prime and see what is the effect on the beats.
Let's increase it 4 times.
Okay, that's very high frequency.
Yeah,
that's
too much.
very high, and you get quite high number beat frequency.
I'll decrease k.
What was initially 0.2?
0.2.
Okay, so now make it 0.1.
Can we not draw a spring and a mass and show the movement here instead of the graph? So, or along with the graph, can we not show the mass moving and what is happening? What is coupling?
The animation part.
Animation
yeah,
part.
Pratik,
Okay.
I have sent the code on WhatsApp.
I saw. So I'll just modify this code and animate it. Okay. So we have all this, and now what we have to do is we have to just put this whole thing inside the eye. Now, okay, have I imported? No. Okay, so there is this from IPython display. We have to import one function named clear output. So what this does is every time this I loop is running, it will plot the point, but it will clear it for the next thing. So you will see how it looks when I do it. Is that all? I think, yeah. That's all I had to modify. Something is wrong. Clear output is not. I didn't run this. Okay.
You may decrease the value of dt.
Yeah. Okay.
Put it to 0.1.
Yeah. Now you can see that this gets animated. So the x limits and y limits are adjusted as the loop goes on.
Now, yeah. So there is an animation technique available. Now, what was expected is in the same frame, time is not increasing, but you are showing that mass is oscillating okay around the mean position in horizontal direction.
Masses are not, but I don't get it exactly. So the X plot, like you just want to see the horizontal.
Yeah, what is, I mean, let us see whether it is possible right now to immediately make that code. If it is not, you can later on send the notebook with that code. But what is expected is, suppose, okay, let us consider this box, and the mass is kept, say, at say 1/4 the distance from left hand edge and say 1/4 the distance from right hand edge, and it is given horizontal. So x is plotted horizontally. So the x of first object will decide how that mass is oscillating horizontally. X of second object will decide the second mass horizontally, and you may connect them with some dotted line as if it is a spring, something like that.
Okay, so you're describing how to make animation. Like
Yes, yes.
I don't think this is possible right now immediately in
That's fine.
Matplotlib.
That is fine.
There is one function. There is one module in Matplotlib named animation. We'll have
okay.
to
So
explore that.
yeah, you can explore that and send it later. The people are with us now, so we can always put it on the group or the classroom. Okay, and but the point is, I mean, that kind of thing is available here.
Yeah,
so
it
that
is
you
available.
can
Yeah.
show that. Okay.
Also,
Then you may explore some extra conditions here, like as k dash decrease, you saw that bit frequency decrease, and therefore the energy took a lot of time to exchange completely. And if the masses are moving symmetrically or perfectly out of phase, then you get normal mode of vibration. So these things can be explored using this kind of simulation.
So can we check for like both k equal to 1?
Both cases, okay. I mean, this coupled spring also one.
Means the spring becomes 1. There is no difference.
There are three springs actually. The first spring is connected to the first mass, second spring is connected to second mass, and there is a coupling spring. So what they have done is they have kept the first and second spring identical, and the coupling spring was initially weak. Now you are saying that make it one, which means it won't be weak coupling anyway. Okay. Yes, it is possible. You can do that. Yeah, you can remove this animation part, and can you plot the graph now? The animation part, of course, you can explore later and put. Right now, don't explore because you have many other things to show.
I had to change k. How many do you want?
You said one. Can you make k1?
Okay, so
can we overplot that?
So don't make it 10,000. Make it 5,000. See what happens.
I think sir, it looks same. There is no difference. Or it is okay.
There is quite different. Yeah, the starting positions are different.
So the ending ones.
Okay, and overplot.
Basically, the graph will have very high frequency. I mean, comparable frequencies which are added together.
So frequency is increasing when the constants are.
You see, the beat frequency is very, very high here. Within just few oscillations, the amplitude goes from very high to very low. Okay. Okay, now go to one
this
thing.
is mass 1, mass 2, and this is both combined.
Okay, now go to one thing and let us do one thing. Make k prime very small, like earlier, say 0.1. Have you made that 0.1? Yeah, and make time 1,000.
Oh, time also 1,000. Okay.
10,000. Sorry, 10,000.
10,000.
Run this once, and then I will suggest one change.
Can you see the plot?
No, not yet.
Now?
Yes, it is visible now. Okay, so you can see the beat frequency. Now, can you make that time smaller so we get it better? Make it say 4000 or so. Okay, fine. This is better. What did I do?
I reduced dt 0.1 to 0.01.
Okay, fine. So this is fine. Now you see the energy transfer is complete. Okay, because the amplitude is becoming almost zero, then again it is increasing. That is because both the springs were identical, spring mass systems, because K1 and K2 were both assumed to be 1 and masses are also taken as 1. Now, so natural frequency of both the oscillators when they are not coupled was same. Now, what you can do is you can make M2 slightly larger or slightly smaller.
I'll take 2 M2.
Okay, you can take 1.5 also.
Okay.
Yeah. Now see what happens to M2. What you have done, M2 you have taken as larger mass, right?
Yeah.
1.5. Okay, so M1 has very small mass and M2 was initially displaced. See, M1 starts from 0. So it does get energy from M2. But effectively the energy of M2 is not falling down to 0. It is slightly decreasing. You can see there is change in amplitude. It is slightly decreasing, slightly again increasing. Okay, and its amplitude is still oscillating between 1 and -1, whereas M1 amplitude is oscillating between say 0.4 -0.4. So M1 you started you had initially given energy to M2. M1 did not have any energy; it was at rest at equilibrium position.
Yeah.
And now the two oscillators are not identical. So as M2 keeps oscillating, M1 does get some amount of energy, okay, but the M2's energy is not effectively reduced. You can do it the other way. What you can do is you can keep this mass M2 same, M1 also same, but instead of giving oscillation to M2, give oscillation to M1 first. I mean first initial distance, so 1 0. So now M2 is heavier, but M1 is
it will be the
given
same
initial
thing,
energy.
Just,
So see again what happens, that M2 is heavier. Even then it starts getting energy because initially it did not have energy. Okay, but M1 is not losing energy much because it's not complete transfer of energy. Their natural frequencies are different. Okay, so and also the displacement of M2 is smaller in this case. Earlier it was about 0.4, now it is about 0.2. Okay, and what it means is being heavier, it is getting displaced by less amount because it will have more inertia. Yeah. So these things you can play with. That when the two oscillators are not identical, the resonance transfer of energy will not take place. If they are identical, resonance transfer will take place. One completely loses energy, other completely gains energy. Okay, and the system goes back and forth.
So can we check at which mass difference there will be a negligible change in amplitude of one of the mass? Heavy mass, heavier.
No,
we just saw, right?
What you can do is you can value, we are varying K also, na? Right? So make K also 1.5. No, sorry, you are not using 3K values. Your second K is fixed.
Yeah.
Can you make 3K?
So this is the K of the center spring.
So can you make 3K and put that in equation?
3 values
Three
of K,
values.
you mean?
1.1. See.
Okay, so 1 and 0.1 we have.
And it will change in the expression down.
In the acceleration, we'll have, this will be for K0.
and K2.
We'll have to separate
See,
these.
for A0, it will be K0 and K2. The coupling spring is K2 now. And for A1,
okay, then let's put it in that order. The coupling spring will keep it in between.
okay, fine.
So coupling spring in between. So 1, 0. K1, K2, K3, like that, right?
Okay, that is fine. Then A0 is K0. The A0 expression is correct. A1 expression will be minus K2.
So minus K1 here in
K2,
this case.
K2. Yeah.
Correct. K2 plus.
And that is correct because that is the coupled spring.
Yeah.
Fine. So now you can run this. So this is the same system that the two springs have same force constant, but one has different mass. Now what you can do is make M1 and M2 say 1 to 1.5, then first K0 also 1 and K2 also 1.5.
1.5.
So here now what will happen? The omega for first oscillator is root of K by M, so it is 1 by 1. And for second oscillator, it will be 1.5 by 1.5. So again, now it is in resonance. Okay, but masses are different.
I'll make a diagram so that people can visualize. Might be confusing for some.
Right.
So
this is K.
This is our
K0.
This is our K0 index. Should give more space. This is our K0, and this is our M0. This is our K1, M1, and then we have K2.
Yes.
Okay, so I have put the values. I'll run this now. Yeah.
Now you see again there is complete transfer of energy, almost complete transfer of energy, because the two oscillators are identical. They have identical natural frequency. It's not complete, but almost complete. Professor Modi, you want to suggest something?
What
Extra
if we
cases?
have higher coupling spring constant?
No, this is fine, Mahesh.
So as coupling is increased, you see the beat frequency is increased.
Okay.
Okay, I think now you can go to the fractal plots, but that is more fun.
Yeah, well, now Jigar will take over and he will show you the damped oscillation part, and then we'll begin with fractals.
Yeah, so I'll just go through the damped oscillation code and I'll explain
what I suggest, what I suggest is you run the code and show the output. Okay. Rather than explaining the code right now, because you're going to share this notebook, right?
Yeah.
So,
yes. Okay.
So we'll run the damped oscillator one, and then we'll go to directly Hanan one.
Right. So this is the code for damped oscillator, and this is the following output.
you can change the conditions under damp, critical damp. You can change the value of B and show that.
So I have first, okay, is this visible? Okay.
Yes,
Do I
now
need
it
to
is
zoom
visible.
more?
Okay. You can zoom in more bit.
Okay, so I've set the K value as 0.4 and B value as 0.2. So the equation of motion is nothing but MA is equal to minus KX minus BV, and V stands for the velocity. Here I have taken all the initial velocity as 0. I mean, the mass is the same, but I only have these three variables for different values of B. And these values will be updated later in the time loop, and you will get the following output. So B square greater than 4mk is overdamped, which is in green, and B square is equal to 4mk is critically damped, which is yellow, and B square less than 4mk is underdamped. So if you want, you can change the values of mass, or okay, say for example B is 0.8, and see what that happens. Yeah. So as you can see, the
you are plotting all three curves. So where is the plot of what changed now?
Okay, yeah. So I have changed the plots here. So I have added the B value here. So
Okay, can you plot only one at a time, and you change the value of B, and we'll see that how things change. Just show one plot at a time, which is at hand.
Yeah. So I'll just this as well. And, this, okay, I can just do this. Don't have to fill everything. Yeah.
So this is underdamped. Okay. Now you increase the value of B, and let us see what happens.
Okay.
No, don't put that label at all.
Okay. Value of P is okay. So increase the value of B to 0.4 from 0.1.
Yeah, so it is damped more. It is underdamped, but it is coming down to 0 almost within one oscillation. Okay, you can increase it to say 0.5 from 0.4 or 1. Okay, it is still underdamped a little bit because it's going below 0 before coming up again to 0.
So we can verify that by plotting a grid.
So it is visibly observed. It is, yeah. Okay, you can increase B.
Okay. Say 10.
And you want to increase, you increase in steps. Okay, but now it is fully damped. Fine. Make it 2 and see what happens. Make it 4, see what happens. Okay, so this is critically damped because it doesn't go to the other side. They're not critically damped. We need to check between 1 and 2. Somewhere it will get critically damped. Okay. So you can play with this kind of thing.
Yeah.
You can go to the next simulation that you want to show.
Okay. So the next would be Henon map. Let's just I'll start from a new cell. the new notebook. That will be useful.
So now we are coming to the fractal plots, which are basically using certain equation. You iterate the x values or y values, or you may take a complex plane and you iterate the real and imaginary components, okay, with the help of certain set of equations. Either it could be just one iterative equation, or it could be coupled iterative equation, like what Gita is now showing Henon map. So x and y values, so the next step y value and x value will depend on the earlier step x value and y value. So these are coupled equations, and they give you ultimately the values converge to certain, not certain point, but certain region, and that Jigar will explain or demonstrate rather.
Yeah, so for Henon map, these are the iterative equations. So so the map takes a point xn and yn in the plane and maps it to a new point in these from these equations. So okay, let's just create a basic map. First, you start with importing NumPy, and then matplotlib. And then you define a function called Henon. You can put any name, but it would be advisable if you do this. Then okay, so it will take the x and y values and the constants a and b in the equation, and it will return the following. So it will return the equation 1, that is 1 minus x, 1 minus a times x square plus y. Also, another thing it will return is b times x. Okay, so for, let's just say that we have this initial condition that a is equal to 1.4 and b is equal to 0.3, and then we go with the initial condition of x is equal to 0, and the initial condition of y is equal to 0, and then we make two lists. Both are empty. This will be useful for appending values in the for loop. So the for loop is in the range of say 10,000 for, yeah, and missed the in, yeah, and now x comma y will now be updated by previous x comma y values along with the a comma b values, and then we need to append the x value list with x.
You missed equal to.
Oh yeah, yes, my bad. Then y values dot append y values, and then we plot the figure. So figure fixed size, and say it is 10, 10, and then we scatter plot x values on x-axis and y values on y-axis. Say the color to be black, and the size of the points to be say 0.02. Okay, and then finally we do plt.show and see if our graph works. Yeah. So is this visible?
Yes. Nice graph here.
Yeah.
Okay, so can you explain what is happening as it goes on iterating?
Right. So in this for okay, so here in this loop, the initial, say for example, I is equal to 0, the first part of the loop, we have set x and y as 0. So the function will return 1 minus a times 0 square, that is just 1, plus y, that is just 0. So the function will be called in each time step and update the following values of x and y. Since the the x value is now okay, so the next x value is nothing but 1 minus a times x square plus y, and the next y value is nothing but b times x.
Okay, so when you call this Henon function, basically it is giving this iteration, which is given in the iterative equation. Now, come back to the plot, and to understand why it is fractal, one may imagine is probably it started plotting at some point at the, say, bottom, and then it slowly went up, and then it went up and it came back, and so on. That doesn't happen. So instead of plotting 1,000 points, if you say 10,000 points, if you plot only 1,000 points, let's see what we get.
Okay. So if we plot 1,000 points, what we get?
So you get the points exactly in the same region, but there are less number of points. Okay, you plot now. Can you make S larger?
What larger?
In the scatter S. In the scatter S, you make 0.1 or so. So you see, there are only 1,000 points, but they are all distributed along this particular curve. Okay. Now, if you make it 10,000, just see what happens. The density of the points increase. So points are basically taking places in between. They are not taking exact places, because moment they will take exact place, the next iterative equation will ultimately come to the same point, and the plot will stop. So what is happening is, if the density is increasing everywhere, what it means is it goes on filling up some intermediate spaces in between. Okay, that is one of the property of fractals, that it optimizes the usage of volume. Whatever volume is available, now this is volume available in 2 dimension, so it optimizes and goes on putting values in the same place, but it fills up. So yeah, he is going to show some other fractals, but right now they have not done everything. Okay, but we want to explore first some nature of fractals. So is it possible to make it 1 lakh and see what happens? Yeah, so whatever you do, ultimately the points are plotted only in this particular region. So this is the curvature where it goes on filling up the gaps. Now, can you zoom in some region and see what happens?
Yeah, that would be, yeah. So the next step is zooming in. We'll just create a new cell. Everything till here would be the same.
What is the significance of this curve fractal? Like where it is seen or used, or it is just
originally, Henon got this when he was studying the motion of stars. I mean, theoretically, he was doing that, studying motion of stars in a galaxy. So what he did was, as the stars are going to move under the influence of gravitational force of all other stars in the nearby region, these stars, he took one section, and what we call Poincare section. So Poincare section means you take a section at one particular place, depending on the period, and then you see from where the stars are moving. And he observed that if you take certain number of stars and you go on taking the Poincare section, the stars start filling up area in a only particular region. So which is basically an indication that star motion is effectively chaotic, but chaotic doesn't mean random. So chaotic means it will follow certain kind of pattern, and it will go on filling up the intermediate space. But there is a kind of predictability in a sense that we can surely say that star will pass around this particular region, Okay, but there is uncertainty implying that you will not know exactly where the next point will come. Okay, so there is going to be uncertainty, but it is not completely random uncertainty. It is you still have a degree of predictability even when the system is chaotic. So it originally came in the problem of astronomy.
But sir, like if we talk about stars, then doesn't it revolve around the center of the galaxy? Then how it could be performing this
Because
kind of
they are also under the influence of, I mean, when he built the model, they were also under the influence of gravitational force of other stars nearby. So you see, this is also observed in the planetary motion. The motion of planets is not exactly the same ellipse. That shape slightly changes because of the motion of the planets, motion of the gravitational force of other planets. So it is not exactly the same ellipse every time. Okay, it slightly changes, and that's where the original question of whether entire solar system is stable or not was discussed by mathematicians, and Lagrange showed that yes, it is stable in a long time domain.
Okay. So basically, we can assume that the path, the fractal that is in shown here, each point is a one star, and it could be any star.
Yeah, it could be, it is the same. Yeah, it could be any star, but you are taking the intersection at regular interval of time, that where the star is intersecting, and that plot you are seeing. So it is not a continuous time domain plot. It is the what we call Poincare section plots, which means
Okay, sir.
you take intersection of star along a plane at a regular interval of time, and then you go on stacking all those points one over the other. What you observe is it's not random distribution. It forms some pattern.
Okay, sir. Thank you.
Welcome.
Right, so I'm just making this quick code for magnification. I'll explain this once I just see if this is better or not.
You can quickly explain what you have done, that box size and
So block size is nothing but the figure size, and the x limit is now the point I want to focus at. So p comma q is the point I want to focus at. In this case, it is 0.5 and 0.2. So these points will be at the center of the figure, and I have adjusted the x limit so that they are in the center. I think let me just clear this. Everything is fine. Let's see. Okay. Magnitude. Yeah, so this is zoomed out in fact, but if I change the magnification to say 14, it will zoom a little bit in, and if I change it even more, say 40, then it'll be giving me these lines. More than that, I have to increase the density of the graph, or just say that increase the size. That will be good. And if I say the magnification is 70, this is what I get.
so what you observe is those lines, as you start zooming in, start showing even parallel lines. So you just zoom into old value of mag equal to say 4, no, not or 10. Okay, so you observe certain pattern over here at the center, maybe mainly 2 lines, but you zoom in, now make it 100. And you start seeing multiple lines. You can make it 200 or 400.
Okay.
And you may increase S.
So that's it.
So you start seeing that multiple lines are appearing, which means, and it goes on adding points everywhere. And make it now, instead of 1 lakh, make it 1,000. Let's see whether there are any points here in this region. Yes,
I'll
so
increase
there
the
are some
point
points.
size.
There are some points. Yeah.
Yeah.
So we observe some points. Now make it 10,000. So you start seeing a pattern. Now make it 1 lakh. And the pattern gets filled up. And you can make it 10 lakhs. It will take time to run. It will take.
Should have
It will
decreased
come.
S
No, it
size
will
to-
come. It will come. It will come. Because see, it has come. Yeah. Okay. Can you move to the next fractal then?
Okay.
And anybody has a question, you can ask. But Varun has asked some other fractals. Yeah. So some other fractals. Lorentz map you can show. And you have
Yeah,
planned something else, then you can show that.
Yeah, I will show Lawrence map.
I'll just Pratik, you can take over and show
Yeah.
Lawrence map.
Lorentz map was developed when he was studying simple weather modeling. So he took parameters for pressure, humidity, velocity, like those, and he came out with some difference equation, and he plotted those with iterative method.
Yeah, I'll
to
write
get,
the equations too.
yeah. If you can copy
So
paste, that will be
I'll
better.
just copy paste. Yeah, that will be better. So the screen is visible, right?
Yes, it is visible.
Yeah. Oh, sorry. Yeah. So these were the equations. So this is the Lorentz map. So what basically he did was these are the three equations. They are called Lorentz equations, and this is just a variation in dx, dy, and dt with some of these parameters. So there's sigma, rho, and beta. They all depend on. They are actually Prandtl number, Rayleigh number, and this depends on what system you are considering, some physical dimensions of the system. So as Sir told that he was studying atmospheric temperature variations and pressure and everything. So now we'll see how to visualize these patterns. So let's start by importing.
So again, we are using the Euler's method here to solve this.
So let's take some initial values of x. Now I have taken these values by trial and error and by looking at the looking at the Wikipedia pages and which diagram appears fancy, and I've chosen values accordingly. You can change these values and see what happens and how the pattern changes. So we will create two empty lists to store our x values and y values. Our time step, let's say it is 0.001, let's take, so it will run quickly. Now our sigma value will take 10. our row value will take 28. I took 28 because the plot for row 28 looked good. And I'll take B value. So this beta is it's usually taken 8 by 3. So I'll take 8 by 3. And we'll vary these parameters and see how it changes. So for now, we'll take these values. So 0 to 300 and in steps of dt. So let's put these equations now in our loop. So dx dy dt. So I'll just name them dx dt. So this is sigma multiplied by y minus x, then dy dt is rho into x, rho into x, and x into z. I just opened the brackets, nothing else. Yeah, and then we have dz dt, which is just b into z minus beta.
xy minus beta zn.
Oh, sorry. X into y minus b into z. Okay. Now I'll append these values. So x will be whatever the initial value of x plus the dx dt into dt, and y will be y plus
This is Euler integration method.
dy dt into dt, and we'll append xt dot append. We'll put x values in xt and y values in yt. So yeah, now we have our all values. We'll now plot a basic figure. Let's say 5 by 5. Let's take a small plot so it runs quicker. DK 100. We'll increase these values later and look at the intricacies of this. So
About
xt
z,
versus
dz
yt.
by dt.
Yeah, I will add that later. So I'll come to it later. Let's see how it looks in xy plane first.
But even in xy, z is coupled with these, right?
What one?
Where are the xyz equations? So the equations, xyz equations.
These.
Show the
equations.
show the original equations.
Yeah.
So you see, z is also coupled with xy, and y depends on the value of z. So if you do not iterate z, then you are not getting this figure. You have to iterate all three and only then plot xy.
Okay, then I was going to do it later, so let's do it right now itself. I'll create zt also, and I'll add z values also.
You will have to add z values because it is incorporated in dy by dt.
No, dy by dt has z value which we have already set, so we don't.
No, but that's not a constant. That's not a constant. That z also evolves with time. And that third equation, z equal to z plus dz dt into dt,
okay. Yeah,
will
I
evolve.
get it. I get it. Yeah. Okay. I thought that. Okay. Yeah. So now we have xt is done. Yeah. Okay. Let's say 0.8 line width, and let's see how this looks first. Okay, I'll decrease the line width. Yeah, so this
Get
is
it
how
up.
it looks.
We are
Is
not
it,
able to
is
see
it
fully.
clear?
No, it has not yet come fully.
Now?
Now it is there. Yeah, beautiful plot.
Okay, so now I can increase the number of points and play with it, increase the resolution, time step, and it will look
Here
better.
actually you can show, when there are less number of iterations, what is happening and how the plot goes on building up.
Yeah, okay. So let's say I take 100. Oh, sorry.
Have you changed dt? You don't have to change dt. You, I think, increase
DT is
dpi,
same.
therefore it is taking a lot of time.
Yeah, now is it visible?
No, now it is visible. Yeah.
Yeah, so I decrease the number of points, so it doesn't look that filled.
Okay.
So by increasing
You
the
can
time
show
steps.
yz.
Yeah, okay.
This is xy. No?
Yeah. I'll put it in subplots so we can see side by side everything.
Hello, sir.
Yeah.
Yes.
Sir, I did exactly the same coding which you did, and I'm getting a straight line.
Straight line.
Yes.
You can send the code on WhatsApp. I'll check
Yeah.
it.
Okay, one second.
It also looks like two galaxies are merging with each other.
Yeah. So this is in XY plane. Let's take second as YZ plane and then XZ plane. Let's see how it looks. Okay, what? 1 or 3 positional arguments. Okay, what is happening exactly? Uh, one row, 3 column. That is right. Yeah. X 0, 1, 2. Okay, why is this not working?
There are only 2 numbers. Is it because of that?
No, this shows that it will be in 1 row and 3 columns. That is correct.
Okay.
Actually, I had done this before. Let me just think.
Pratik, what's the issue?
It's showing it should take 1 or 3 positional arguments, but 2 were given. Oh,
Are you
subplots.
plotting column wise?
In row.
Yeah, so do it 3, 1.
That will be 3 rows and 1 column. I need 3 figures side by side like that.
Okay.
Okay, wait. I think you're right. My logic was wrong. No, see, this 1, 3 was correct.
Okay, okay.
But I don't understand why this is not working. Float object has no attribute plot.
You can write some plot thing.
Okay, fine. Let's not waste time on this. I have shown you on XY plane. Let's see on XZ and how it looks. So yeah, this you must have seen the butterfly pattern. So on XZ plane it looks like this, and on YZ plane it looks something like this. I'll increase the number of points actually. Let's say 500 we have. DPI also 300. Yeah, so this is the famous pattern that is this visible?
Not yet, fully.
Yes, sir.
Yes.
Okay, so shall we move to
Yes, move to the next one.
plotting it in 3D?
Huh.
Yeah, so for plotting it in 3D, we'll use we'll define a function, Lorentz. So let's say it's dx, dy, dz. Just a moment. I will define a function, Lorentz, which will take values of x, y, z, sigma, rho, and beta. And we'll say for x dot, that is dx by dt, is sigma into y minus x. Our y dot is
So can you increase the font size?
You can zoom in on the
yeah,
code.
sorry. Yeah. Is this okay?
Yes, sir.
Yes.
Minus y, and we have z dot. Z dot is x into y minus beta into z. And we'll return all of these values. So return x dot, y dot, and z dot. Now let's define our time step. So 0.01. Hello, am I audible?
Yes.
Okay, I think my internet is having some issues. I got a warning. Okay, so I'll continue. dt is 0.01, and let's say the number of steps we take 1000, 10,000. Let's take 10,000. Now to store the values of x, y, and z, we'll define an empty array. So we'll define it such as np.empty, and the length of that empty array should be equal to number of steps. Now it is not exclusive, the number of steps, so we'll have to put number of steps plus 1, so that we'll get 10,000 empty values, else we'll get 9,999. And similarly we'll do for y and z. We'll store our values in this. Now let's set our initial values. So x0 is 0, y0 is 1, and z0 is 1.5. And for our for loop to append, we'll say x values we need to create these extra empty lists so that we can append the for loop values in this and then put it in our xyz main empty arrays. So now that we have done this, let's start with the loop. For I in range, the number of steps that we have decided. For I in range number of steps, so the x dot values, y dot values, and the z dot values will be taken from our function which we have defined, the Lorentz. And the order of parameters is the xi value. So for I equals to 0, it will take the initial values and then it will keep on changing them. Then yi values, then zi values. And then we can put the sigma, rho, and beta values. So from above we'll take sigma. We had taken 10, rho was 28, and beta was 8 by 3, which is around 2.667. You can write 8 by 3 to it. No, it doesn't matter. So now we have our x dot, y dot, and z dot values. Now next step to do is to iterate over them. So it will go to the next index, that is x1, and it will put the initial. So this will be x0 plus whatever the x dot value is into dt. Similar thing for y and z. And just copy paste this twice and change wherever it's required. So for the next element in y, it will take the previous element of y and it will multiply it with the y dot into dt. Next element of z, first element of z, z dot dt. Now that we have these values, we'll have to append them to our x values lists. So x values dot append xi, y values dot append yi and z values dot append zi. So yeah, that's about it for appending values. And now I'll plot. Now what I'm doing is I am putting the plot, the whatever the code for plot is inside the for loop itself. So by putting this inside the for loop, it won't plot all of the points immediately. It will point each point as I iterates. So we'll see sort of a slow animation happening. So let's see how it goes. So just a moment. Sorry about that. Yeah, sorry. So we had to plot. So PRT.figure fixed size. Let's take 5, 5 and DPI of 300. And we have to mention in this that this is a 3D plot. So this is the syntax for that. Add subplot, and we have to say the projection is 3D. And that's it, I think, projection 3D. Now we'll plot the values. So we have ax dot plot. We have to plot x values, y values, z values, and let's set our line width as 0.5, and let's put some limits on our x and y axis so that it doesn't move while it gets animated. So set x limit from -20 to 20, say. Copy paste and change the limits for y and z. Now I am setting these values by trial and error. I plotted and saw that if it fits or not. Now after this, what you can do is you can save your figure.
All this will be in loop?
Yeah. So you can save your figure in whatever your address is. Here, put your address, and what you do here is put your number of iteration dot png. So that will be the name of each image that will be iterated. So you can save this and you can make a video out of it later, but I'll keep it out right now. I'll keep it commented out. But what we'll do here is we'll see the plot. And we'll have to use the clear output function from IPython. So clear output weight equals to true. Have I imported that or anything? Yeah, I have. Okay. So let's see if this works. It's done, I think. Yeah. Too many values to unpack. Expected 3. Yeah, now you see, now this iteration is very slow, but do you notice the blue line that is increasing?
No, show it. We are not getting full. Right now it is there.
Yeah, the blue line is it's increasing with every iteration. So now this is very slow because this is happening for each iteration. Now you can see it will speed up as it goes towards the attractor. So it will take a lot of time. So because these are 10,000 iterations. So what you can do is
Can you reduce the time gap?
Okay. I'll reduce by more. Let's say dt is 1. No, that is going out of bounds.
No, not that. Here, wait time. Can you reduce wait time?
Reduce wait time. This?
Yes.
Okay, that it's not actually waiting. It's just okay. This function is not like it will wait for the next value. So that animation speed is your processor speed, how fast your laptop can plot.
Okay.
So what this does is, if I remove this and I save each and every figure, then what I can do is I can use another function save to video that Jigar had created. And from that save to video, I'll save all these files in some folder. And then I'll use that function, take all those files and make a video out of it. So
Okay.
I did that last night. So shall I just show that?
Yeah, better.
And
You can just show that. Yeah.
yeah, and we'll send the save to video function. I don't need to, we don't
Right.
need to go into that. We don't need to understand save to video
Yeah.
function. It is
Yes, you can show the. You can share this code because we'll take this as the last thing. We
yeah,
are overshooted time.
yeah, okay. So I'll just show you the animation.
So do we need to install IPython? Because in my it is saying no module named IPython.
Yeah, you'll need to install pip install it, or you can download it from PyPip.
No, Pratik, they have Conda installed, not Pip. We'll have to see uh, how do you install that in.
Uh, Acha, okay. Then you open your Anaconda prompt and you can just type conda install IPython. It will do the same. Conda is just an environment, like pip is a package manager. So
You
yeah, is
can
this we?
also,
Yeah,
Pratik, can you show that you can interact with this 3D plot by just simply including one line that is percentage matplotlib above every code, so that it pops up in a new window and they can interact with it.
yeah, okay,
That will be useful.
yeah,
And
okay.
yeah,
I'll
this
now
was
do. Yeah, I'll
this.
do it in this one.
Uh, it's useful for interacting with 3D plots. You have to
Okay, where did it appear?
try restarting the kernel.
Yeah, okay. It appeared in another window. I will show. Yeah, so it appeared here. Is this visible?
Yes.
Yeah, so you can interact with this. You can zoom in some particular area, or you can pan it. Is this visible or not? So you can see the fine structure here.
And if possible, you can also do it for the 3D plot. So you can rotate and revolve the 3D plot as well, if
Yeah.
possible, quickly.
Okay, yeah, I'll do
And
it.
just remove that animation from that 3D
Yeah.
plot. So
I'll have to take this out of the loop.
yeah.
So this thing out of the loop and clear output here and percentage
Is
matrix.
the screen visible to all? I'm not getting any change.
Yes, sir, it is visible.
Okay, are they changing anything? Because it is not visible here.
Yeah, I'm changing the 3D plot thing. I'm removing it out of the loop, and so we can see it in a other window. So is this visible now? This 3D plot?
Well, I'm not able to get it. I don't know. Now it is there.
So now you can see in 3-dimensional, it looks from this angle as if the points are overlapping, but in 3-dimensional they are not. You can see by rotating it.
Is everybody able to do this? And just simply add percentage matplotlib above all your code, restart your kernel, and a window should appear like this.
So that we can then stop now at this point.
I'll just show
we'll
this
take
animation
some
video
questions.
which I created last night. The quick, the 10,000 plots that I did.
Yeah, just show that then.
Yeah. So this is how it looks when you save all the figure and you use that create to video function, save to video function.
Are you doing it? I'm not able to see any change here.
Yeah, I'm playing the video. Is it not visible?
Sir, it is visible.
Sir, it is visible.
Okay. My net today is...
So I don't know how to share this video with you because it is quite huge. It became about 300 MB. So you can do it yourself and save it on your local system.
Sir, how we can make the video? We can.
Yeah, there is a function save to video. Jigar has created that function, and we'll put it in the notebook that we'll share with you. So you have to just put your path where you have to save and where you have to retrieve the files from. Make sure you put that path carefully, and then you can use the function.
Okay. Thank you so much.
Yeah. So yeah, this is it.
Yeah.
Yeah,
Sir, we are
thank
done.
you. We'll meet in the afternoon session for the validation.
Yeah.